Welcome to the second tutorial session. We're quite happy to have Marco Tomamichel from CQT and National University of Singapore. So today he will talk he will tell us about from one-shot to asymptotic quantum information theory. Please feel free to ask questions during this session and ask them directly to the speaker, and he will repeat them to everyone. So as a reminder, there's no food or beverages allowed, and the masks are required like in all indoor activities. Without any further ado, let's have the speaker start the session. Thank you.
Good. Okay. Yeah. Thank you very much for having me, and it's really a pleasure to speak to you here about some topics that are really close to my heart, to my research. I would have preferred to speak before Richard, now in retrospect, because he really put my presentation skills to shame. But I still hope that you will learn something and at least get some intuition, more intuition about the structure of quantum information and what we do in quantum Shannon theory. Okay, so and let's get started. So in the title it says information theory from one shot to asymptotics. And the basic idea behind this is that traditional Shannon theory or information theory, usually it considers situations where we have some unrestricted resources, mathematically at least. So, for example, we can use a channel as many times as we wish, and we are just interested in the rate at which we can transmit information over that channel. But it's an asymptotic result, where really we take advantage of the fact that we can use the channel many times. Now this is often, I mean, in reality, obviously we have a finite number of times that we will use the channel, for example. But even so, this asymptotic approximation is usually very good. And this has to do with the fact that we can quite effortlessly nowadays pre- and post-process classical data in huge chunks, and thus really work in blocks that are large enough so that the asymptotic approximation works. Now there are exceptions to this, even in classical information theory. For example, if we look at a wireless system where we might want to send short packets so that everybody gets a fair share of the time, and you don't have to wait for your stream to update and so on, right? So you want to send data in short bursts so that everybody gets an opportunity. And then these asymptotic approximations don't work well anymore, and that's why also in classical information theory people have been looking at finding corrections to these asymptotic results. Okay, so but now, since we're in the quantum conference, we can obviously observe that, well, with quantum information, we are in an even worse situation, at least for now, because it's really impossible to manage large amounts of quantum data, at least for the foreseeable future. So we are in this regime where the asymptotics themselves are theoretically very interesting and give us some beautiful results, but maybe we can't really reach them at the moment, and we want to look beyond that. Now, specifically, a little bit a different situation is in cryptography. We just don't know anything about the structure of the information that we are dealing with. So usually, in channel coding, for example, we assume that the channel is memoryless, so the channel doesn't remember what was sent through it just before. And that gives kind of a structure that we can use to analyze the asymptotics. In cryptography, usually we don't want to do that. We want to assume that the eavesdropper has full control over their quantum memory. And for example, if we have multiple rounds of communication, the eavesdropper might act on each round differently or coherently on all of them. And so we don't have the IID structure that we usually hope for in information theory. Okay, so what does this mean? This means that when we look at quantum information, we need to be open-minded about how we measure it. Because while in classical information theory, essentially, as we will see, most things boil down to just a few entropies that we need to know. So we need to know the Shannon entropy. We need to know maybe conditional entropies and mutual information. And they are good enough to characterize all the asymptotic problems that we're interested in. But if we want to go beyond this, and in this finite resource regime, then we need to look at different quantities that might be more appropriate for certain tasks. Okay, and so in this tutorial, I want to kind of introduce you to this. Well, first of all, I will introduce you to these quantities and also how they're used. So my main focus is really going to be on the toolkit, which I hope will be useful for you to, well, maybe in your own research or maybe also just to understand other talks at QIP. And not so much on the individual results, although I will discuss some particular applications and also mention in various places some talks that will be at this QIP that cover some of the topics that I'm discussing. So here, this is just a little selection of talks at this QIP that use tools from information theory. Now it's a very, it's an incomplete list, but it's just some of them that I found when I was looking through the papers and seeing what they're actually in their proofs, what tools they're using. So the first one, and I will always kind of mark them. So if you see this, the red color, then that means that's a QIP talk. I didn't look up for you when it will be. You have to find that out yourself. But the first one uses it for deriving some results in quantum cryptography and complexity theory. That's one area where these entropies are often used. Other examples are in statistical physics. They're often very useful because they allow you to measure, for example, correlations. So here are 3 papers that I found that take advantage of this information theory calculus. And even in other fields, like in quantum machine learning, because information theoretic tools are often very helpful when you try to show that something's impossible. So they're kind of a little bit of a destructive tool often. If you want to show that something is impossible, then these entropies often give you tools because you can use their monotonicity and things like this to show that certain quantities will not increase, and that will help you in making such arguments. Actually, we heard this morning one such argument where an impossibility result was shown by relating a problem to channel coding and then using that, we cannot communicate more than 1 bit in a qubit, so the Holevo bound. So the tools are very useful for various problems, not just Shannon theory itself. Good, okay, so this is going to be the structure of this tutorial. So the first part, which hopefully will take me through the first half of the tutorial, is really about the structure of quantum information and how we measure it. So we talk about classical and quantum information, and And we introduced tools that allow us to deal with additive and multiplicative errors. The second part is really then focused on a particular problem, which maybe you can think of as the core problem in quantum information theory, and it's this quantum hypothesis testing. So we'll talk a lot about that and how to analyze this problem in various different ways. So that's where we go from where we look at the one-shot bounds and then go to asymptotics and see what has been done in recent years. And in the third part, we then discuss some applications of this to two tasks, channel coding and, in fact, entanglement-assisted channel coding and randomness extraction. These are just two examples where we can employ these techniques. And finally, I would like, if time permits, to discuss some open problems that I'm hoping maybe one of you might be able to solve, and I can then listen to a talk about this at the next QIP or maybe a couple of QIPs later. So that would be my hope to motivate you to try to solve some of these problems. Okay, so so for the remainder, I'm very happy to receive questions at any time. I try to explain things step by step, and I hope you can follow. If not, please do ask questions. I'm also very happy to clarify. So I should have enough time. I have more slides than Richard, but I think I should easily be able to get through them. And so if you have questions, that will only improve the process. Good, okay, so just as a reference, I try to give references on my slides, except when it's stuff that is from my book. And I will also put these slides online afterwards. So if you have any comments on them, if you feel like there is a citation missing or something like this, just write me an email and I add that. Or if you find typos, I would also be very happy to receive your comments. Okay, so the first part, the structure of quantum information, as I call it, this is about entropy measures and in various forms. So Philipp Feist at some point had a nice poster, I think it was also from some QIP, that calls this the entropy zoo, because at some point there were so many entropy measures that I think almost nobody could follow anymore what all their meanings are. So there's a poster with many arrows and connections between them. I'm trying to give you a bit of a guided tour through that zoo and try to convince you that at least some of them actually have operational meaning, and we'll try to explain to you why you should at least a little bit care about them, or why they might be helpful for your problems. Okay, so but let's start with the easy stuff, classical information, right? If we want to have an intuition about quantum information, we probably better should first understand classical information. And it's actually not so easy to, I mean, if you just try to conceptualize what is information, it's not so clear how to do that, at least for me. Intuitively, I find it much easier to think about entropy. Entropy is a measure of uncertainty. So the entropy of a random variable is somehow a measure of how uncertain I am about the outcome of this random experiment. And so one way to measure this is using what is called the surprisal, which one can arrive at by just requiring it to have some simple properties. So you want the surprisal of two independent events to be just the sum of surprisals. And you want it to be monotonically decreasing in the probability. So if you a less likely event is more surprising, right? So that's a simple concept. So you can define from this notion of surprisal, which is what Shannon did in his seminal work. And then the entropy is simply the expectation of this surprisal. Okay, so if you ever wondered, you've probably all seen this formula for entropy. One way to see it is just as the expectation value of the surprisal. Now, if you look at it this way, then it's kind of natural to ask, well, why do we only care about the expectation value of the surprisal? Maybe we want to know more about the distribution of the surprisal. So one measure that people use very often in cryptography is the so-called min-entropy, and this is just the minimum surprisal, or in a sense, a worst-case surprisal. It tells you, in cryptography, you want to make sure that the randomness that you produce is difficult to guess for an observer, for the eavesdropper, for example. And so this is a worst-case measure, the minimal surprisal that the eavesdropper could have about your random experiment. Right? Because the eavesdropper will always guess the most likely outcome. And so it's the worst case that really matters here. Okay, and so that's one way of looking at it. Or more generally, we can think about the full spectrum of kind of information that's contained in this surprisal. And one way to do that is to look at the cumulant generating function. So that's just a tool from probability theory, not so important now, but the cumulant generating function gives you the whole distribution, or characterizes the whole distribution of the random variable. And if you rewrite the cumulant generating function a little bit, you get the Renyi entropies. And I think they were also mentioned in the morning. So Renyi entropies are defined here. And they're just a function of, again, the probabilities. So all entropies are functions of the probabilities of the different outcomes and not really the value of the outcomes, right? This is an important thing because the value doesn't tell us anything about whether some event is surprising or not surprising. And yes, so that there are important special cases. The min entropy is one that we get when we let alpha go to infinity. And the Shannon entropy we will get when alpha goes to 1. And there's also the max entropy, which is just a logarithm of the support, which we get when alpha is 0. Good, so we have a lot of these entropies. Now, I want to convince you that we really need them. So this is a little example. So we have two different distributions. So one of them is a flat one. So if I just plot, I guess this would be the probabilities. This is a flat distribution, whereas the other one has a peak. All right, so we have one large, and then 4 events that have small probability. Now, if you look at these two random variables, we see that they have the same Shannon entropy. Okay, you can just compute it. I chose the values nicely so that everything turns out well. So then they both have entropy 2, but obviously they are different distributions. So how do we see this? Well, while the Shannon entropy, for example, characterizes how well we can compress a sequence of such outcomes of such random experiments. Okay, and so asymptotically then we know that for both sequences, one chosen from X and one from Y, we can compress them to the same size with vanishing error. So that means that's what equal Shannon entropy tells us. Now, if we, however, want to look at a single instance of this random variable, and maybe we allow for a small error, let's say the error is a little bit less than 1/8 to make it work, that we allow, then it makes a difference whether we get x or y, right? Because if x only has 4 different outcomes, so 2 bits are enough to store that outcome anyways. But for y, we have 5 different outcomes, and so what do? We kind of have to, if you want to store this in 2 bits, we will make an error with probability 1/8 at least. Okay, we can kind of like put 2 of them together into one bin, and then we just get 4 bins, and we can code that in 2 bits. But generally, we have a problem. So if we are interested in the behavior for finite size, even for compression, then it matters what distribution we have, and it's not just enough to look at the Shannon entropy. The other extreme, so that's kind of what the max entropy actually tells us, what I just discussed. Okay, we need log 5 bits to compress a single copy of y. Well, we can't compress it. That's the point, because all of these events have large enough probability, so we don't have any typicality or anything that would allow us to compress. The other extreme is the min entropy, and here the question is just which random source would you want to use in your casino? Obviously, you want to use the uniform one, because it has min entropy 2, and it's difficult to guess the outcome of this experiment. You will just get it right with probability 1/4, whatever your guess is, right? They're all the same. However, if y is used as a source of randomness in your casino, so you're playing roulette or something, and you take this randomness, then I would guess that the most likely event will occur, and whatever deterministic, so this event here, and whatever deterministic function you then do from there on, I can just do that myself as well, and the outcome that I will predict is whatever I get when I plug in this particular event. Right, so this is the guessing probability here is actually 1/2. With probability 1/2, I will guess the correct outcome, and everything else that you're going to do with this, your deterministic function that will tell which number will pop up in roulette or something like this. Roulette is probably not a very good example, because I don't think the casino has control over where exactly the ball will end up. But any kind of maybe an online casino is a better example where you really need this randomness. Okay, so you want a small guessing probability, which means a large min entropy. Okay, good. So that's entropy. Now, entropy is a property of a single distribution. Yes, there is a question. If you know all of them. Oh, yes, the question was if you know all of the Renyi entropies, can you reconstruct the distribution? I think in the discrete case, yes. But I'm not so sure if this is like mathematically true in all cases. But if it's a discrete random variable, I think that the cumulative generating functions allows you to reconstruct the full distribution. It's a good question, probably. I haven't really thought about this, but I mean, I think the answer to that is known. I just don't know it right off my head. But I would not be surprised if it were possible that you have a compact set around alpha equals 1 should be enough. Okay, very technical question. So let's get back to entropy. So now we go to relative entropy. So we're interested in two different distributions and essentially the difference of their surprisals, which is the log likelihood ratio. And if we take the expectation of that, we get the relative entropy, or classically it would be the KL divergence, which I wrote here. I mean, I'm not going to usually be very technical about how things are going to be defined, but I just want to introduce it the first time. I wanted to be precise. So this quantity essentially goes to infinity if P is not supported in the support of Q. So if P, if there is a value for which P of x is positive and Q of x is 0, then this will go to infinity, which you can see from the way it's defined, because we're then dividing by 0. So one has to take that into account. But in a sense, it's a measure of distance between two distributions. So it's 0 only if they're actually the same. And there is also, again, we can do the same thing and define a Renyi divergence, which also can be interpreted as a function of the cumulant generating function. Good, so why am I introducing this relative entropy? The reason is because I don't want to talk about all kinds of different quantities all the time. And this relative entropy or KL divergence can be interpreted as a parent quantity to all the things that we are usually interested in. So I can write the entropy, for example, as the difference between, this is just log of the support, and then the relative entropy between the distribution of x and the uniform distribution. So this is uniform. Okay, so if P x is in fact uniform, then the second part will be 0, and I get the maximum value of the entropy, which is just a log of x. And on the other hand, if Px is deterministic, then one can do some computation and see that this goes to 0. Similarly, we can define conditional entropy. Conditional entropy is a measure of, so entropy is a measure of uncertainty about the outcome of x. Conditional entropy is a measure of conditional uncertainty, which means it's the uncertainty you have if you have access to y. So if y is correlated with x, that might reduce your uncertainty about x once you know y, and then this conditional entropy would be reduced. Okay, the third quantity is the mutual information. This is now really a measure of correlation, and you can see that directly here in the sense that the mutual information is related to the distance between the joint distribution of x and y and its marginals. So if you have, if they're independent, then this would be 0. And if they're very correlated, then this mutual information will increase. So then the joint distribution is far from the product of its marginals. And similarly, conditional mutual information can be seen as a distance from your joint distribution now over 3 random variables and a Markov chain where both of, well, in this case, x and y can be produced from C. So can be seen as channels acting on C. Okay, so all correlation between X and Y. So on this right-hand side, all correlation between X and Y is going through C. This is what Markov chain tells us. So we're looking at how close we are to the Markov chain, and that gives us the conditional mutual information. So this is kind of nice because it tells us that if we understand divergence or relative entropy, then we understand everything. So we can kind of focus on this for the moment. Good. So, okay. So I introduced some quantities now, which we know that they're kind of useful, but why exactly are these the right definitions? And there are two kind of ways you can approach this. One is to say, well, they are nice because they have nice mathematical properties that are very useful for us. And here are just some examples of properties. I said it's positive. It's always, it satisfies, for example, these data processing inequalities. These are one for the conditional entropy and one for the mutual information. So these inequalities themselves have kind of an operational meaning. For example, the first one tells us that the conditional uncertainty increases when I forget about one of my random variables. So if I don't look at y, then obviously I have more uncertainty about x than if I look at y. So that's very, any measure of uncertainty should have this property, or of conditional uncertainty should have this property. And so we call this also, we call all of them data processing inequalities. Because you can think of forgetting about y as some data processing. This inequality would also hold if you just do some operation on yc. You just compute a function of it, for example. That will only increase the entropy you have about, at most, increase. Good. So, okay, so that's one way to look at it, nice mathematical properties. The other way is to say that they have operational meaning. So we've already discussed compression, which gives operational meaning to the Shannon entropy, and also the guessing, which gives operational meaning to the min-entropy, for example. Now, I just want to remark that obviously these two things are in some sense tightly related, because often to derive these operational, the operational meaning of a quantity, you actually need all of these mathematical properties. On the other hand, and here is a little exercise, if you have the operational interpretation, then often you can derive mathematical properties from it. Because since these quantities characterize some particular task, they must have particular properties. So as a little exercise, you can try to show that this inequality holds for entropy via thinking about source compression.
So there is a question by Arthur Dominguez, like on slide 13. Is this last measurement a way of classifying Markovianity of quantum systems?
So this is classical. So in this particular question of Markovianity of quantum systems, this is a very non-trivial problem. But yes, the conditional mutual information also in the quantum case can be interpreted similarly, but it doesn't work as nicely. For example, this expression here in the quantum case doesn't make sense. The problem is here, the way it's written, I mean, this is a very good question, actually. Very, very deep question, though. The way this is written, I'm starting with a distribution on C, and then I'm applying two channels. One creates X from C, and one creates Y from C. If I would do that for quantum states, okay, I can start with some state and then try to do some map that brings me to a joint state, but then I've destroyed C somewhat. So I cannot just apply a channel and then apply another channel on C. Classically, that's not a problem because C just stays the way it is, right? You can look at it as many times as you want. But quantum channels, they wouldn't commute. So it's not even so clear what this expression would mean in the quantum setting. So for mutual information, conditional information, we will see things generalize quite nicely. For conditional mutual information, there are a lot of questions still. So maybe we have not as good an understanding of it. So did anybody have a chance to solve this problem? Sum of the entropies needs to be smaller than the joint entropy. Yes? Yeah.
I guess what we're technically saying is that they have some correlation, then the entropy is lower. So the left-hand side, we're looking at them together, and on the right-hand side, we're looking at them separately.
Yes, I mean, operationally, the way you could argue is to say that, okay, I need to compress X and Y. One thing I can do is just compress them separately. I first compress X, then I can do that using h of X bits of memory per instance of the random variable. And then I do Y, I get h of Y. And that is one way of compressing the joint distribution or the joint random variable. But I could do better, right? If I use the correlations between the two random variables, I might be able to compress them much better. I mean, the extreme case is where if Y is actually equal to X, then I just need to compress one of them and can get back both, right? So I can use the correlations to improve my compression. And if h of X is supposed to characterize how well I can compress, then it must satisfy this inequality. Right. Okay, good. So we spend a lot of time on classical information, but I think it's important to kind of set the scene. So now we can start thinking about quantum information and how should we measure it. Well, as I said, the KL divergence takes a very central role. So let's try with the KL divergence first. And what we can think of, like maybe the simplest thing to think about is just, well, let's find some expressions involving quantum states that in case of diagonal quantum states reduce to the KL divergence, right? That is one property we certainly want to have. It should reduce to the KL divergence for diagonal states. Now, the issue with that is that gives us lots of different ways of doing this. So you probably know this one, Umegaki quantum relative entropy. That's the one we are using nowadays. And so we will argue later on why this is the right one. But that's not the only way we can write this. We can, for example, take the two logarithms together and just have some product. Here, if we evaluate this for diagonal states, we get the same thing. And we can do that even in two different ways, because the ordering of operators obviously matters if they don't commute. So, and then we could even split them more into, maybe have here the exponent 1/4, and then kind of split it up in little chunks, multiply them together. That there are infinitely many different ways in which we could find generalizations of this format to the quantum setting. So that doesn't seem to help us, seem to get us very far. Now, one more fruitful approach is to find generalizations that preserve at least some of the important properties of these functions that we want to have. And the important property here is the data processing inequality. And the data processing inequality for relative entropy simply states that if I apply a channel to both arguments, then the relative entropy can only decrease. Okay, so this operation, this kind of means that, you know, if the relative entropy is a measure of how well you can distinguish between the two states, then if you apply some noise to them, then it will be harder to distinguish them. So they kind of come closer together, right? We have the same property for trace distance, for example, or fidelity. And it's very important to have this property to make sense, to really interpret something as a metric or a measure of distance between states. If suddenly you apply some noise to it and they get further apart and are easier to distinguish, that wouldn't make sense. So we want this data processing inequality. We also want it because it's kind of the source of, so if we take this viewpoint of the parent quantity that we had before, and we define our conditional entropies, mutual information, and so on, using this, this viewpoint, then this data processing inequality, in fact, implies all the other nice properties that we have. So here is just one example. Entropy, we expect it to be to increase when we apply some mixing operation. So if we apply some process, here is a bistochastic map on a random variable x. So the bistochastic map is one that, well, in quantum it would be called a unital map, one that increases the noise, or a uniform noise in some sense. If we apply such a map, we expect the entropy to increase. Right? This increases our uncertainty about the outcome. Like a depolarizing channel would be one example in the quantum setting. So we can show that this inequality holds just from properties of the relative entropy. So this is just shown here. We just rewrite it in terms of the definition that we use, and then we know bistochastic map will keep the uniform state distribution intact, and thus we get the inequality that we want. This is just one example, but all of these things that I mentioned before, these data processing inequalities for conditional entropy, mutual information, and so on, they all follow from the data processing of divergence if we define things in the way I suggested in the previous slide. Okay, so we want data processing. But now in the quantum setting, data processing is slightly different. We want them to be monotone under completely positive trace preserving maps, so quantum channels. And there's a way in which we can define such extensions that preserve this monotonicity. And I mean, there's just a generic way thing we can do. We look at two generalizations. So this is kind of a down symbol, means that this is the minimal extension to the quantum setting. And the minimal extension we get when we look at measurement outcomes. So we have a definition for classical, for commuting states. So now we just take the supremum over all measurements of our quantum state and define this to be our measure of, a new measure of quantum divergence. Okay, this is also called the measured relative entropy. This is measured relative entropy. Oh, sorry, here I used the word divergence here for everything. And the other thing we could do is kind of the opposite, is looking at preparations. So we just start with two distributions, P and Q, and want some map that if applied to P gives us rho, and if applied to Q gives us sigma. And this is another way of defining a quantum divergence in terms of what we already know, which is a classical divergence here. Right, these two things here are known. These are classical quantities. And it turns out that if we define things like this, it's kind of nice because then we can show that any quantum generalization that satisfies monotonicity under completely positive trace-preserving maps, or this data processing equality, must lie strictly in between these two quantities. So, okay, so that's kind of a mathematical way of trying to come up with extensions. But yeah, obviously seeing that as a measurement and preparation is also quite operational. But these are now optimization problems. So that's a little bit annoying. Let's try to simplify them. So this one is not so important because it hasn't really found an operational interpretation yet. Although I could also put that as an open question. If you can find one, that would be very interesting. So this is what we call the maximal extension. And it has a closed form, at least for alpha between 0 and 2. We can write down a closed form of this. And one special case is this Belavkin-Stasevsky relative entropy, which was, I think, in the early years of quantum information, people thought that maybe this is the right way of writing quantum relative entropy. So this, it has a closed form, so we don't need this optimization, and it has turned out to be useful at least for proofs, not so much directly for operational tasks. But it has some nice properties because it's related to matrix geometric means. Another thing here is that for alpha larger than 2, I think it's not known what the closed form expression of it is, or if there is even this one. Good. So okay, so that one was maybe a little bit less important than what I'm talking about now. So because this quantity now is used widely used in quantum information. So we have this minimal or measured relative entropy. It's interesting because it satisfies data processing, but it has one disadvantage, namely it's not additive on the tensor products. So what we can do is regularize it. And if we regularize it, it turns out that it has a closed form. So the regularized quantity has a nice closed form, and that is called the sandwiched Renyi divergence. And that one is quite useful. It was first used to show a strong converse property of entanglement breaking channels. It will also show up again when we look at the hypothesis testing later on. Okay. So this limit is actually highly non-trivial. I'm not going to go into details and trying to convince you of proofs. But actually to show these results, they require a lot of advanced linear algebra. So this particular proof requires that we show that this quantity, so this sandwiched relative entropy satisfies data processing inequality. So that gives us one direction of the bound. But to show that required some heavy tools. And for the other direction, we use some tricks that are also very common in information theory, which is this pinching inequality, which essentially tells us that if we try to make two operators commute, one way to do this is to pinch one of them. So pinching means that I take some density operator here, sigma tensor n, and I look at its the spaces with the same eigenvalue and the projections onto those. And if I then just apply these projections on another operator, that's called pinching. So it removes all the off diagonals except those inside these projectors. And this makes the two operators now commute. And we kind of come back to a classical problem. So this is a really useful trick. The pinching inequality tells us that somehow this is not too destructive. It's quite destructive, but not too destructive. The reason for that is simply that there are not so many, if we have this ID structure, sigma tensor n, there are not so many different eigenspaces. The number of different eigenvalues of sigma tensor n actually scales polynomially in n and not exponentially. And that property is often used in many arguments in information theory.
So there's a question from the online attendees by Gofrain Bel Haj Aisa that asks, density matrices can be expressed with many compositions. What kind of procedure do you do to choose one among all these compositions and apply the measure?
Density, sorry, I'm not sure I fully understood.
So the density matrices can be expressed with many compositions. What kind of procedure do you do to choose one among all these compositions and apply the measure?
So, I mean, maybe there's a confusion here that the density operator is a unique thing. Then you can decompose the density operator in different ways into pure states. But we never needed this. Because all of what I've done is directly in terms of density operator. So that the density operator is unique. Or I probably misunderstood the question, but that's all I can answer. Okay, now just to kind of make this maybe a little bit closer, get this a little bit closer to you. So I showed you this abstract definition of the sandwiched divergence. Maybe I should say the reason it's called sandwiched is here, because rho is sandwiched by sigma, some powers of sigma, and then that's where the name sandwiched comes from. And obviously, this is a very particular ordering of the density operators that is not at all unique. But yeah, so it's an interesting class of quantities. For example, because we find many well-known special cases. For example, the fidelity appears when we plug in alpha equals 1/2. So in a minus log of the fidelity. Another one is the so-called max divergence, which essentially is an operator inequality and is also used to characterize robustness and things like this. So this is another special case of these sandwiched divergences. Good. So you think, okay, so we have defined now our Renyi divergence, so we're done, right? Sadly, that's not the case. There are actually is more than one family of Renyi divergences that have operational significance in quantum information. And depending on the situation, you need a different one. And so these other ones are actually have been around for a bit longer. They were introduced by Petz originally. And they have a much simpler form. In this case, we don't have any complicated sandwiches. We just take rho to the alpha and sigma to the 1 minus alpha. It's just essentially the first thing you would probably try if you just try to generalize the classical expression. And it also has operational meaning. But it has one disadvantage. So the sandwiched one satisfies this data processing inequality from 1/2 to infinity. This one satisfies data processing from 0 to 2. So it's not the whole range of alphas where these quantities have the kind of the nice properties that we want. And here, in particular, for alpha larger than 2, it does not satisfy data processing. So, I mean, there are counterexamples. Now, this is still a somewhat active field of study. So, at some point, there was introduced a whole 2-parameter family of Renyi divergences. I mean, they're obviously a 1-parameter family in alpha, but people introduced 2-parameter families and try to find out which of those satisfy data processing. And there is one talk at this QIP, a variation method and its application in quantum information theory that actually discusses, in particular, this topic and how one can show these data processing inequalities. Essentially, it's about showing joint convexity, which is equivalent. But there are mathematical questions that are non-trivial, that took a while to sort out, to find out which of these quantities, in fact, satisfy data processing. So it turns out there are more quantities satisfying data processing than there are quantities that have operational meaning. So if you just care about this, then this Petz family is one of them, and the other is the sandwiched one. Good. Then a final remark. So these quantities also have nice limits. So the two families, they limit when alpha goes to 1 to the omegaki relative entropy that we introduced. So that was the first one, the one that you're used to. So they limit to that. And we can also look at the derivative at 1, because that's, in a sense, that's related to the second cumulant, or the second moment, central moment of the log likelihood ratio classically, and the quantum generalization is what comes out when we look at the derivative. So, okay, so just quick overview. We have seen we have this maximal divergence, which is the blue one, and then we have the sandwiched one with the tilde, and the bar is the Petz. So these are the two, the green and the red one. You see they match at alpha equals 1. They give us the relative entropy, and then they're tangential at this point as well, so they have the same derivative. This is just what I was talking about before in a picture. So just evaluated for a particular example. Now the dashed lines are kind of regions where these quantities no longer satisfy data processing. Okay, so we have this spectrum of Renyi divergences, at least two families that seem to be important. Now, that's a start. We will later see where they pop up operationally. But before we go there, I mean, originally the goal was to introduce these divergences, because then we can define all kinds of other quantities as well, like entropy and conditional entropy and so on. So if we do this for entropy, in fact, the generalization is unique if we require that they remain non-decreasing under unital maps. So if under unital maps they should at most increase, then the definition of quantum entropy or any quantum entropy is unique, and it's just given by these formulas here. Now for conditional entropy, things get a little bit trickier. One reason for that is that there are actually two ways in which we can write conditional entropy. So one is the one that I mentioned before. Now there's a slight difference. So this is the identity. It's written on the slide already. This is the identity here. So I just kind of absorb this log term into the relative entropy because I'm allowed in relative entropy to the second parameter doesn't need to be normalized. So all the nice properties still hold if that's not normalized. So I just absorbed it in here. I have an identity to write it a bit more compact. But the point is that I can write it in two different ways. Either I put in the marginal here, rho b, or I in fact maximize over any state here. It just turns out that for the relative entropy, so at alpha equals 1 is in this case, this maximizer here turns out to be exactly the marginal. So I can write it as an optimization problem or just plug in the solution. Okay, that doesn't seem a very useful exercise. The problem is that if I go to Renyi divergence, these things might not be the same thing anymore. Okay, I might need to make a choice. But first, a little bit about conditional entropy, because it's an important object to kind of get an intuition about in the quantum setting. So one thing we can see from this definition, right, and as you know, we can decompose it as a difference of two entropies. This is actually how it's usually defined in textbooks. It's defined as the difference between the joint entropy and the entropy of the second system. But these definitions are equivalent. Now, if we do this, then we see something interesting. Maybe if rho AB is pure, then this entropy of AB is in fact 0. So the entropy of pure states is 0, but the entropy of the marginal might be arbitrarily, might be large. It might be a maximally entangled state, and then h of b would just be the log dimension of the system, of the marginal. So it can get negative, right? So what is our intuition about entropy? We said entropy is a measure of uncertainty. Now what is negative uncertainty? Doesn't make a lot of sense. So we have to be a little bit careful about taking the classical intuition to the quantum setting. So the negative entropy is really a property that is very quantum. In a sense, the uncertainty is negative because we know more than everything about A, if we have a purification of it. We know everything about A when we measure it in the X basis. We also know everything about A when we measure it in the Y basis. And we also know everything about A when we measure it in the C basis. Right? If we have entanglement, we have this property that is much stronger than classical correlation. In a sense, whatever measurement you do on A, you can find out the result by looking at B. So this is a much stronger form of correlation than what we have classically, and that's why it's negative. Why it's negative because we defined it in this particular way, but that's how you can try to make sense of why it's negative. Good. So now what happens when we try to define this thing for any conditional entropy? And we will need any conditional entropy. So it's not just an exercise. We have lots of choices now, right? We said we have two families that make sense, and then we have two different ways of either maximizing or not maximizing. Now I'm only suggesting these definitions. You could come up with other definitions. So if you defined entropy as the difference between conditional entropy as a difference between joint entropy minus entropy of the marginal, you could try to do the same thing here for any entropy. Any entropy of the joint system minus any entropy of the marginal. Now this I would suggest you don't do. And the reason for that is because then you don't have data processing. So this property that if you do some operation on the side information that will actually increase your entropy, that is really a fundamental property of a conditional entropy. If you don't have that, then I think we are not talking about conditional entropy. And if you define it as this difference, then you wouldn't, this property would not be satisfied. And I mean, one can show that it's violated, in fact. Even classically, this is already the case. But if you go via this relative entropy type of definition, then you automatically have this property. And so the kind of intuitive understanding you have of conditional entropy is correct. It's a measure of uncertainty given some side information. Okay, so these, but you still have four. It's like nobody wants to deal with so many different definitions. Yeah, so I'm just gonna leave them here. And show you something that I find very amazing. Well, first of all, maybe for those who don't care so much about Renyi entropy, I always start with the usual, for Neumann entropy case. Entropies have this very amazing property that if you take a pure state and you look at the conditional information entropy of A given B and A given C, they add up to 0. So what does this tell us? It tells us that even if one of them is negative, or if one of them is negative, then the other must be very large to compensate for that. This is what we use well, it's one way to see what we use in quantum cryptography. In quantum cryptography, we are always trying to ensure that an eavesdropper doesn't have information about what we're doing. So eavesdropper must have high entropy. And we can do that in quantum mechanics essentially because of this relation. Because if we can ensure that A and B, or Alice and Bob, have very high correlation, for example, because they're entangled, then that ensures that nobody, even somebody who holds the purifying system, the whole rest of the universe, if you want, cannot have a small entropy. So you can see this as kind of this duality relation as kind of our main tool for doing quantum cryptography, or one of the main tools. And yeah, it's an expression of monogamy of entanglement. Now it turns out, and this is more for maybe more interesting for people like me who kind of are amazed by these things, we can write down duality relations for all of these Renyi conditional entropies as well. So this hints at that we probably are on the right track. So we can do it for pets. Here this down arrow, that's from the last slide, in case you followed my advice and ignored it. That this is just about whether we maximize over sigma or not. So we have one relation for those, then we have one for the sandwich ones. And this is kind of the one where, this is maybe one of my open questions for you. If somebody can explain to me why this holds, then I would be, I really want to better understand it. I cannot understand why this holds. So this connects actually the sandwiched and the pets definitions via this duality relation. And this hints at some deeper structure of these quantities and kind of singles them out, right? So these two are connected. That's the two that have operational meaning as well. They're connected through this relation. So there must be some deeper structure that, as a person fascinated by mathematics but maybe not able to solve it, I would want to understand. So if somebody can tell me why this happens, then that would be great. Yes, and one use of these things is we can use them to derive entropic uncertainty relations that are then used in cryptography. So, right, they give us a quantitative expression of uncertainty relations. This I haven't done here, but it kind of follows from this duality rather directly. Good. Okay, so then, and the other thing we want to discuss is mutual information. Mutual information is this measure of correlation. So we're comparing a joint state with the product of its marginals. We can obviously also do that in a quantum setting. But now we can torture ourselves with even more definitions because for this typical case, so with the alpha equals 1 relative entropy, we can actually either do one minimization over the first term, over the second term, or over both. These are all the same. And if we go to Rennie, then they're all different. And we don't know which one to pick. And also we have, again, the two families that we started with. So, okay, we're not going to do that. That would be now, I think, 8 definitions or something. We're not going to do that, but these two seem to be the ones that may be the most interesting and have some appear in channel coding. Okay, good. So I'm not going to say much about this. Now, the final thing that I just need to mention, because essentially my PhD thesis was about this topic, smooth min-entropies. So smooth min-entropy is a measure of uncertainty as an entropy, but it's a variation of what we would get. So if this sandwiched infinity entropy is the quantum min-entropy, and if we now optimize this over a set of closed states, we get the smooth min-entropy. Now there is an whole calculus built on this. Smooth min-entropies are also used in classical cryptography. And we will see, I will talk a little bit about randomness extraction and why and then the smooth min-entropy makes an appearance there. So it tells us how much uniform randomness we can extract from a source. But we'll get to that. Good. So that was all I had for the first part, actually. So we have some time for questions, if there are any.
I have a question. So when you have all these different like the Moranian something that it's not sure how to
So one thing that I kind of mentioned on the side, I'm not sure that completely answers your question, but I was referencing the talk. So what you can do is you can see them both as a part of a bigger family of divergences. But I'm not sure that solves the problem, right? Now you have even more of them. And then they're just, these two families, the pets and the sandwich one, are instances of this, or, yeah.
So I was asking this because you were saying, like, for example, this duality relations. It seems you get these duality relations for like specific combination of parameters, like alpha times beta equals 1 over alpha, things like that. And I was thinking, are these different relations just instances of the same actual fixed relation, but with some change of variable?
Okay, yes, so the question is whether one, maybe by a smarter parameterization of these things, one could maybe see that it's all the same in some sense. No, I don't think so, because it's quite complicated. Actually, these parameter ranges here have meaning as well, because I mentioned this only on the side, but these quantities, they are not always satisfying data processing, for example, only for certain parameter regimes. So if I have pets with the bar, then it would be between alpha 0 and 2, where it satisfies data processing. Outside of that range, the quantity is meaningless in some ways, because it doesn't follow our intuition, and you can't use it in proofs because it doesn't satisfy the properties you need, and so on. So alpha between 0 and 2, if you look at this relation here, alpha plus beta equals 2, it maps the interval 0, 2 onto itself. And the same happens here with 1 over 2 to infinity. This relation here, 1 over alpha plus 1 over beta equals 2, maps this onto itself. So yeah, I don't think there is a hope to actually simplify it, because the quantities are really different. I mean, well, that's not entirely true, because what I mentioned before is that I hope that there is a kind of a structure there that I just don't see yet, but I don't see it yet, and it's not obvious to me. Yeah. So there is hope that there is some structure. I mean, there must be, otherwise, why should they be connected? There must be something that relates them.
Okay, any other questions? Right, so let's thank the speaker, and we'll have 30 minutes of coffee break. Yeah.
Okay, welcome back. Glad that most of you are still here. Now we're gonna, in the second part of the tutorial, we're gonna explore some applications of all of these quantities that I just burdened you with, so that you see that they're actually useful for something. And so the first part is going to be on quantum hypothesis testing, which is maybe the most fundamental problem in quantum information theory in some sense. At least we can relate many of the other kind of problems that we're interested in, like channel coding or privacy amplification. We can relate them to hypothesis testing on a very fundamental one-shot level. So if we understand hypothesis testing, then we are a big step towards understanding also other problems. So that's why a lot of focus will be on this. And then we'll move on to other problems. Okay, so what is binary quantum hypothesis testing? So first we will consider the case where we only have a single copy of a state, and we have two hypotheses of what that state might be. It might be either rho or it might be sigma, and we don't know which one. So what we can do is do a measurement, right? And the measurement is a binary measurement. We can design it such that measuring some POVM element T indicates that the null hypothesis is true, which is that the state is rho, and 1 minus T, so that the other operator, or identity minus T, would indicate then the other hypothesis. Right, so depending on our measurement result, we make a decision which hypothesis was true. So if we do this, then we can define two types of errors, the first and second kind. The first kind is, in this case, the null hypothesis is actually true, but our measurement didn't click, or we measured the POVM element identity minus T. So we will decide that the alternate hypothesis is true, even though the null hypothesis is true. So that's the first kind. Second kind is just the opposite. And obviously what we're interested in is to find tests that minimize these errors. Right? We want to find tests that are in some ways optimal. Now, we know very well this result, so the kind of the simplest case where we consider both of these errors equally. So we're just trying to minimize their sum, or the average error if like both of these hypotheses occur with equal probability. Then we can think of this as an expected error. And this we can compute. This minimization is what gives the operational interpretation of the trace distance. That's why we use trace distance very often, because it tells us exactly how well we can distinguish two states, right? Here, the trace distance is 0. That would mean that it's actually the same state. Then we will make an error with probability 1/2, which is the 1/2 we get here. And if the distance gets larger, then for example, if it's 1, then they're orthogonal, which means we can design a test that perfectly distinguishes them, and so on. But generally, these two types of errors have different significance. Right, you have false positives, false negatives. If you think of examples, for example, in medicine, these two types of errors are very different in their implications. So you want to often treat them not on equal footing, but separately. And in that case, what we're really interested is the region that can be achieved with our tests. So what kind of pairs of the two errors can we achieve? So most generally, that is the question that we care about. And one way to characterize this region is by looking at its boundary. So here we're just trying to minimize the error of the second kind, given that the error of the first kind is bounded to be at most epsilon. So that gives us the boundary of the region. We're trying we're trying to find the best test that satisfies that the error of the first kind is smaller than epsilon. And this kind of is a nice formulation. I mean, if you look at it, it's a semi-definite program, can be efficiently computed and so on. So we can actually deal with this quantity fairly well. Now, if you look at the literature on information theory, often this quantity is actually expressed in a divergence-like form. If we take minus log of this function, then it behaves in some senses like a divergence, and we call this a one-shot divergence. We'll encounter it later on. But it's essentially just a way to write down this boundary. One advantage of this thing is that it also satisfies data processing. So this is also operational in the sense that if you apply noise to your two states, then they become more difficult to distinguish. So the region is contained in the other one. Good. So we can pictorially look at this. So what we're interested in is really this region, which would be all of this here, of allowed pairs of errors. And then this red line would be the boundary of this region. Right, so the 0 point is the one where we both errors would be 0, so that one we can usually not achieve. But then we have this region which needs to be convex that we can achieve, and geometrically the trace distance would just be when you try to find a tangent on this region for a line that satisfies that alpha plus beta is a constant, right? And that constant will be then the trace distance. So you're just trying to get as far away as far as possible in this direction to get the trace distance. Okay, so that's one-shot hypothesis testing. We have one copy, and we can kind of understand this very well, and it's, as I said, a semi-definite program to compute this line. So good. But the question we often consider is the one where we not just have one copy of a state, but we actually have many copies of the state. And we want to understand now how do these errors behave asymptotically as we get, if we have many copies available. So that's the kind of the typical setting we consider in information theory. We're not happy with we're interested in the one-shot setting, but then really the question is, how does this scale when we have many copies? And this is, if n is large, I mean, we have seen this morning that, well, we kind of prefer to do tests that act on single copies and then kind of build up our statistics from that. Here we don't do that. So here this is very impractical because the optimal test on n copies might actually really be a joint measurement on n copies of the system. So in this setup, we don't really care about how difficult it is to implement such a test. So that is what I kind of mentioned that at the beginning as a motivation. Maybe we want to get away from this n going too large because it's completely impractical. Maybe we can say something for intermediate n and get more realistic results or more practical results. Although one has to say that still, even for n equals 100, this still seems very far out of reach at the moment to really achieve these optimal measurements. Nonetheless, we can look at this when n is very large. We know that any two states, unless they're actually the same, will become almost orthogonal at some point. So they become more and more orthogonal. Trace distance goes to 1. And we can distinguish between these two hypotheses perfectly well in asymptotic limit. So the question that we're left to answer is, well, how quickly do actually these errors go to 0? So how quickly can we make them go to 0 using optimal tests. So one way to characterize this is again by pairs, but now it's pairs of error exponents. So this, I mean, notation is a little bit sloppy because I'm not saying, well, it's not even clear that these limits necessarily must exist, but let's just ignore these aspects. So what I'm looking at here is I'm taking the error, I'm taking the logarithm of it, so that gives me an exponent, and then I'm assuming the exponent grows with n. So it's exponentially in n. And the minus I also take out. So when I get some positive value here, it means that if this limit is a positive value, then it means that the error is e to the minus n times that value. Okay, so if I guess if I call this, how do we call it, kappa, then the error would be 2 to the minus n times kappa. Okay, so that's just for the kind of intuition of what these things are. And we can do, again, a plot. And if you notice, it's the same plot. I just changed the labels. The curve is actually the same, but now the error exponents are actually in here. So that's the achievable region now. Because obviously, an error exponent of 0 means that we're allowing a constant error. There is no exponential decrease, and it's difficult to make these error exponents large. So we are constrained in some region of possible error exponents. And there are several now results, some of them very well known, that restrict this area. So one of them, we'll discuss them individually, but one of them is the quantum Chernoff bound. This is what we get when we require that both exponents go to 0. So this is the symmetric case where we actually look at the average error and ask how fast does the average error go to 0. So this is the Chernoff exponent, and geometrically we just cross this line with the diagonal and look at that point. Now the other results that we kind of know is maybe the so-called quantum Stein's lemma, which gives us these 2 points. There we require, we allow one error to be constant, arbitrarily small but constant, and then ask how fast can the other error go to 0. And that is given by the relative entropy. So I'll discuss these results in detail, and then the Hoeffding bound gives us kind of the whole region in between. Okay, so what do we know about these things? So first, maybe the quantum Chernoff bound. So here we are interested in the average error, but now we do a test on n. So this Tn just stands for test on n copies of the state, and we want to understand what is the best possible exponent that we can achieve here. Now, one way of looking at this, so if you're not an information theorist and you just try to solve this problem, one thing that you might come up with is to just, we have already this expression in terms of the trace distance. The trace distance, however, has a problem that if we take n copies, we know it's going towards orthogonal, but we don't really know how it scales. It's not multiplicative on the tensor products, right? So if you want to analyze it, one way is to go to fidelity using the Fuchs van der Graaf inequalities, and you get something like this. Okay, this shouldn't be, just be a comma here. So we have the fidelity between rho and sigma, and the fidelity is multiplicative. So there we can just, the tensor n, we can just take it out of the fidelity. And then we see that this thing scales exponentially in n. So if we rewrite this, it gives us a lower bound on the exponent that is just this expression here. So now I just rewrote the fidelity again as a sandwiched relative entropy just because I like sandwiched relative entropies, but it's a fidelity. The other reason I did this is because I want to compare it with what is the actual result here. So the optimal exponent has been found, and it's given by this expression here, which is an optimization over these PETs relative entropies, alpha relative entropies that we've seen. Okay, so we are optimizing them between 0 and 1, and you can see that obviously this optimum is larger than the particular point at alpha equals 1/2. And then we also know that the PET's relative entropy is larger or equal to the sandwiched one, because the sandwiched one we've seen is the minimal one amongst all the Renyi relative entropies. So this means that this lower bound here was certainly correct, but it's not tight. Generally, you can do this optimization, and that gives you really the expression for the optimal exponent that can be achieved. But again, to achieve this exponent, you will have to do joint measurements on n systems. It's not clear what you can do. Well, I mean, we can say something about what we can do if you just do measurements on single systems. Then at least you have to replace this d bar with the measured relative entropy, which is potentially much smaller. Because then essentially you're doing classical hypothesis testing after the measurement. But okay, so this is the situation for this Chernoff bound, and it kind of gives an operational interpretation to the PET's relative entropy. Now, the other kind of well-known problem is the quantum Stein's lemma. And the quantum Stein's lemma is kind of the first result in this arena in quantum statistics that really established the relative entropy that we are using today. So this Umegaki relative entropy here. By the way, I'm using divergence and relative entropy interchangeably. But this definition, like, why do we know that it's the correct one? Well, we've seen it satisfies the correct properties, but we also seen that the Belafkin one also satisfies the correct property. It also satisfies data processing. When we try to solve this problem and find the exponent, we get this definition. So it singles out this definition of the relative entropy. So what is the problem that we're solving? Well, it's just a situation where one of the errors is fixed to be at most a constant or limiting to a constant, so we don't require it to drop exponentially. And then we're looking at the largest possible negative exponent that we can hope for, and that is the relative entropy between the two states. Yes?
In this case, is there any constraint on epsilon, like range of the constant? Maybe any
Sorry, the range of epsilon? So epsilon is just between 0 and 1, strictly. You run into problem when you set epsilon equals 0. And then you have to analyze the problem differently. And if it's epsilon is 1, then it just is infinite. Then, yeah, you can do whatever you want. So then the problem is trivial. Okay. But yeah, so otherwise there are no restrictions. It's just a constant. Good. This reminds me that in the break, Angela reminded me that actually my definitions of the Belovkin relative entropy was wrong. I had the ordering of the operators switched. So I'll fix that in the slides that I'll put online. It doesn't really matter because we're not going to use it. Good. Okay. So now we've seen on this plot that it's a whole region, and the region is characterized in the general case by a situation where we want both exponents to be positive, so we want both errors to go exponentially fast to 0. And in that situation, that's called the quantum Hoeffding bound. So we assume here that R is smaller than the relative entropy. That's just because otherwise we're anyways outside the region of interest, right? We saw that the relative entropy kind of gives the boundary. Then we expect one of the errors to drop exponentially with this rate R, and then optimize over the other exponent. And we see that this optimization, this exponent then is also again given by an optimization over Pet's relative entropies. So the boundary is given by this optimization. Now, if you are interested in statistics, just classical statistics, there are other ways of writing this thing that maybe are more directly make clear that these come from large deviation theory. So this is some transform form of the cumulant generating function that really is written here, but we express everything in terms of Renyi relative entropies. But it's really large deviation theory that gives you these exact exponents. And in large deviation theory, you need the cumulant generating function. That's kind of why Renyi divergences appear here. I mean, this is a mathematical reason why, but yeah. So yeah, just for those who carefully read these formats, I mean, I'm putting certain things under the carpet. If you really want technical statements, you need to go to the papers. But one thing that could happen here, for example, is that if R is actually very small, it's smaller than D0, then it turns out that it's easy to satisfy this. So if you put in 0 here, you see that this formula actually diverges and the exponent goes to infinity. But that is expected because if there is an easy test that you can do that will give you a rate R and you never make an error of the first kind. By just projecting on the kernel of root tensor n. So this D0 is one of the Pet's Renyi entropies that we looked at. It essentially, it's whenever rho and sigma have full support, this is actually 0, this relative entropy. If both of them have full support, this doesn't happen. But if rho has smaller support than sigma, then kind of we come into a situation where we can play with this. Okay, so these formulas, I mean, they look a little bit intimidating, but if you think about them, they do make sense. And essentially, you're trying to optimize this Renyi parameter in a range between 0 and 1. Good. So then there's the last result, which I promise you that this sandwiched Renyi divergence also has operational meaning. And so here we're actually looking at a situation where we're outside this region that I described. So we're asking this beta to go to 0 with an exponent that is too large, that is larger than what's given by Stein's lemma. So in that case, what will happen is that the error of the first kind will actually go to 1. So if we require our tests to go have very small error of the first kind, larger than this exponent here, then the other error will have to go to 1. And we can also determine how fast it goes to 1 exactly. So these are all, by the way, these are all equalities. I didn't really, so in all of these slides, these two quantities are the same, right? I'm saying that this operational quantity is equal to this information optimization. So if we are interested in how fast this error goes to 1, then that's given by this optimization here, which looks very similar to the ones we've had before, except that now alpha is larger than 1 and we have a sandwiched relative entropy here. Good, and these results are a bit more recent. Now, even more recent is kind of a further analysis, and this we will see where this really then enters when we look at channel coding and privacy amplification. But we can ask several more refined questions. So here, I'm just rewriting this quantum Stein's lemma. I said this quantum Stein's lemma, we can express it as a kind of asymptotic behavior of this boundary function. And we fix epsilon is constant, but this will now exponentially go to 0, and the exponent is given by the relative entropy. Now I didn't divide by n this time, so that the n is still on the right-hand side, and then I can just interpret this as this limit as that this scales as n times the relative entropy plus something that goes to that grows slower than n. But now what we can ask is, well, maybe we can actually give a more refined statement here, because one of the properties that we see here is that the left-hand side actually doesn't depend on, the right-hand side doesn't depend on the error. Right? Even the left-hand side depends on the error epsilon, but in Stein's lemma it just disappears asymptotically. There's no dependence on the error. But what we can do is we can just further expand this and find the higher order terms in this expansion. And we see that the next order term then depends on, it grows with square root of n instead of n, and depends on this variance of the relative entropy, the divergence variance. So this quantity here. And it also depends on the error. Now, this is also called a Gaussian approximation. because essentially it shows this phi to the -1 is an inverse of just the Gaussian distribution function. So what it tells us is that if this epsilon is very small, then this is negative, and so we can't actually, if we want a small error epsilon, we can't actually really get exactly to the exponential decay n times d, but we have some square of n correction to that is negative. So it's going to 0 a little bit slower. And if we allow for more error close to 1, then it actually goes to 0 a little bit faster than just the n times relative entropy. Also, it gives us corrections on this exponential and those, we'll see how they show up, for example, in channel coding. So there's even more we can do. We can kind of try to get the cake and eat it too. So this Stein's lemma situation was that one of the errors was fixed to be a constant, and the other error went exponentially fast to 0. Now, ideally, we would want both errors to go to 0. But maybe not both of them equally fast. So here we have one error that goes to 0 in a sub-exponential way. So this epsilon n here goes to 0 sub-exponentially. This is just because xn as a sequence goes to 0. And then we can write down, again, this expansion. And we see that we again get some correction on the asymptotic behavior. But now this correction also depends on this sequence that we've chosen for the error. So typically, you could choose here some sequence that, like n to some power. That's larger than -1/2. Okay, so it's just different kind of viewpoints on this hypothesis testing problem, different types of asymptotics. Now, these correction terms, they are interesting in the sense that we want to know what happens for finite n, right? That was our initial goal. So one way to understand what happens with finite n is by looking at corrections on the asymptotic behavior of these quantities. Now those, it's still asymptotic statements, so they're still only valid for large n, but at least they give you corrections on the first order terms. The other approach is obviously to look at the one-shot quantities directly, but those are usually difficult to treat analytically. Like I said, for example, this boundary function is an SDP. That's very nice, but if you try to compute an SDP on a 10-qubit system, then you quickly run into troubles. So those things don't really scale, even for small and these one-shot results. And so corrections to the asymptotics at least give us some indication of what's happening when we go away from n, from very large n. Okay. So now let me say a few words about something that's going to, a talk that's going to be at QIP, or I just want to introduce essentially the topic. Also to let you know that not all the problems are already solved. I just gave you a list of solved problems, which is nice, but there are also a lot of problems that are not yet fully understood. One variation of hypothesis testing that one can look at is so-called composite, the composite problems, so where the null hypothesis or the alternate hypothesis or both of them are comprised of a set of states, and then you're trying to distinguish between whether the state is in one set or in the other set, right? So that's already a variation of the problem. Now, on the sum regularity assumptions classically, then, for example, Stein's lemma still has a very simple form. You're now just minimizing the relative entropy between these two sets. So you're kind of looking at the, if you think of the relative entropy as a metric, which in some sense you can, then this just means that you're looking at kind of the two closest states in the two different sets, right? And looking at their distance, and that is what gives you the exponent. This is kind of natural, what we would expect. But it turns out that in a quantum setting, generally this doesn't simplify so easily, so you need a regularized quantities in that case, and in the work at this QIP, Moshoni and collaborators, they show that even classically, if the sets are not compact, then you kind of get this behavior where the simple formula doesn't work. But there is also much recent progress, so I gave one a reference here on this topic. And so there are many open questions still, in particular in this composite hypothesis case, which is important for resource theories, for example, where maybe you're trying to ask the question whether the state is in a free state or some other state. And then you immediately have a composite problem. Okay, another variation of this that recently looked at is a variation that is maybe a bit more practical. So here we're asking, before we kind of asked always, you get n copies of your state, you do a measurement, and you make a decision, right? So it was it's a one measurement, one decision. It's actually optimal to just do a joint measurement. And you never want to, if you can do a joint measurement, you will do it. You won't just individually measure, and then that's always suboptimal. But here we ask a slightly different question. Maybe we don't fix the number of copies at the beginning, but we kind of think of, okay, so we have an oracle that gives us copies of this state, and we obviously don't want to use too many, but we are happy that if we just in expectation, for example, use n copies, and sometimes might be a little bit more and sometimes a bit less. And then we can ask the same questions of how these error exponents behave in this case and what we can achieve. And it turns out, actually, we can do much better in that situation. So if we just have this little flexibility that in some cases we wait a little bit longer until we make a decision, and in others we might even make a decision earlier. If we have this flexibility, then we can make sure that both of the errors go to zero with the relative entropy. Which means that by just changing the problem slightly, we can achieve this whole square instead of just this little area in terms of error exponents. So this is kind of interesting because it's maybe the more practical setting for hypothesis testing. This flexibility of just asking your experimentalists to prepare one more copy of the state, maybe that's not the expectation value there the number of copies needed is actually the relevant thing, and not, you don't need to fix the number from the start. Okay, so this is kind of one, I think, interesting recent development there. So maybe a quick opportunity for questions. Yeah.
Is there a way to control the concentration on it so we have a good expectation of spread out?
Yes, actually you can achieve the same thing even if you ask for the probability of not exceeding n to be epsilon, let's say, some constant. Yeah, so that has concentration as well. Good. Oh, yes.
So I was wondering, is there any generalization to multiple hypotheses? So more than two.
Oh, yeah, so the question is generalization to multiple hypotheses. Yes, that's also a very natural question to ask. Then in that setting, I think we just know much less. And the questions are also more complicated, right? Because now you have, well, you have you have more than 3 errors that you could maybe distinguish. Like right, the setting, the landscape is much more complex. Yes, the Chernoff bound still, that one still makes sense, the symmetric case. And there is a multiple hypothesis that's in Chernoff bound, yeah, that K. Lee established some years ago. Yeah, so the Chernoff bound still makes sense. The other types of results, there one would have to define exactly what these different trade-offs are that the one is interested in. Yeah. Okay, good. So then I move to the last part. So the applications now of, well, I mean, this was already an application in some sense, but now we're going a little bit more applied. So maybe I should say a few words about the general philosophy of this approach to information theory. So the title is From One Shot to Asymptotic Information Theory. The idea is basically that we can often split our analysis into 2 parts, where in the first part, we kind of look at the problem in some sense, the information theoretic part of the problem, where we relate, or we look at the operational quantity that we want to bound. For example, the number of messages we can send through a channel when we only allow for a certain amount of error. So that's an operational quantity at the number of different messages, I mean. And we can give bounds on those quantities in terms of some, often we can do this by relating it to some information quantity, like a hypothesis testing divergence, also this boundary that I discussed, or we relate it to a smooth min-entropy in cryptography, for example. And that is kind of the information theoretic essence of the problem. And then there's a second part where we just do what we just did with it, because that's statistics. So where we just look at the ID setting and look at different limits. We look at different regimes that we want to analyze. So we can split the problem in somehow in 2 parts. The information theory part and the statistics part. So that is maybe the modern approach to a lot of these problems. And so we're going to look at this now in terms of the entanglement-assisted communication over quantum channels. So for this, I'm going to explain the setting a little bit. I'll go rather quickly through this. So the problem here is we have a quantum channel from A to B, and we say this channel is memoryless, which just means that essentially we have many copies of the channel that we can treat independently. So there's no correlations between the different channel users. The channel doesn't remember what you sent through it before. Right, so we can just think of this as an n-fold tensor product of a channel. And we look at codes that use entanglement. So such a code, you can characterize it by a set of messages that we want to send. So usually we want to optimize, you want to get a large set of different messages that we can send. Then we have a state, an entangled state between Alice and Bob that we can use as a resource for our protocol. That's what it makes it an entanglement-assisted protocol. Then we have an encoding operation, which in this case is just takes a classical input M and then does a map that creates from this part of the resource state as an input. So the Alice is part of the input state and creates the channel input A, which is what we're going to send through the channel. Right, so the message that we're trying to send here is classical, so I just see that as a parameter of this encoding map. And then on Bob's side, in the end, we get the channel output B, and we do a joint measurement on that channel output and Bob's share of the entangled resource state. And this is a P of M, and it gives us an outcome M, which is going to be our estimate of the message, our decoding of the message that Alice sent. But that's a code, a general description of a code for entanglement-assisted communication. So we can put this all together. So we have this entangled state. Then Alice does some code, takes a message, encodes it, sends it through these channels, and then there's a decoding happening on Bob's side. And what we want to do is so we call this M is the message, is a random variable. Usually we choose it, assume that it's uniformly chosen. And M hat is what the estimate that Bob produces. And what we want to do is we want to make sure that this probability of error, namely the probability that M is not equal to M hat, this should be small. Right, that's our the goal in channel encoding. Good. And I mean, this probability, obviously, you can write it down what it is in terms of all these parameters of the code that I wrote down. I won't bother you with this because I think the picture is more useful here. But the general goal in analyzing this problem is, again, about finding trade-offs, right? Because we have different parameters that we're interested in. We want the error to be small, but we also want the number of messages, so the cardinality of this message set, we want that to be large. And obviously there is a trade-off between these two things. And the channel coding problem is about understanding this trade-off. And there are now different ways of formulating this problem. Again, we can, maybe one way to do it is to say that a triple with a rate n and epsilon is achievable if there exists a code that has error smaller than epsilon and uses more than log or e to the nr different messages. So why is there a log? Well, we are interested in the number of bits that we can send. So the rate is kind of the natural thing. N times R is the number of bits we send, and N is the number of use of the channel we have. So R is the number of bits per channel use that we are sending. Right? This is the natural quantity to look at here, at least if we were thinking about asymptotics. Okay, so we can define this region, and obviously we're interested in the boundaries of this region. So one way, that there are different ways of characterizing the boundary, but one way is to say, let us find the maximum R such that R and epsilon is achievable. And we try to understand this quantity for in the one-shot setting, also when n is equal 1, and also for large n. But now if I formulate it in this way, you can see that maybe we are not only interested in the limit n to infinity of this quantity, but actually an expansion around the asymptotic limit, so that we can also say something for a little bit smaller n. Okay, so we'll see how that looks like. Now, what I want to point out here is that these one-shot quantities, they can, I mean, this is the information theoretic part of the argument. Often we can relate them to hypothesis testing problem. That's why I talked so much about hypothesis testing before. Because my goal is somehow to relate these information theoretic problems to hypothesis testing so that I can use then the knowledge I have about the statistics of hypothesis testing to derive the results I want. So here we can use this bound, for example, which tells us that this R for a single use of the channel is bounded by this quantity, which probably does not tell you too much. But if you look at it closely, it looks a little bit like a mutual information. We said the mutual information is exactly this, but just forget about the H and the epsilon. And then what is written there is actually, well, if you ignore the H and epsilon, what is written here is exactly the channel capacity. The entanglement is the channel capacity, because it would be the mutual information between A prime and B optimized over the input states. So it would be exactly the entanglement assisted channel capacity. It's just that we don't have the relative entropy here, the D, but we have this hypothesis testing entropy-like quantity here that is non-asymptotic, but we kind of know that asymptotically it converges to the relative entropy. Maybe I should write that this is related to this minus log of the beta star. That's how I called it before. This DH, I think it was only occurred on one slide. So it's exactly this kind of one-shot hypothesis testing quantity that we've encountered before. Okay, so in a sense, this relates the problem to hypothesis testing, and then hopefully we can use the tools from there to go further in different regimes. There's another way of understanding this is kind of, it's a hypothesis test between the actual channel output, which is what the channel output together with the reference system. So we apply this channel to the A system, and this is one hypothesis. The other hypothesis is that there was actually no channel and we just created some noise. So the other hypothesis is that what actually happened is we used a replacer channel that just took the input and replaced it with a fixed state, in this case sigma. So we're doing a hypothesis test between these two situations, and that is what characterized this. Now, yeah, this is called, at least classically, for classical coding, this is called the Meta-converse, and the same name in the quantum setting, because it's kind of, from this bound, we can derive all kinds of other bounds. It's a very tight relationship. It's a converse. Converse here means that it's an upper bound on the rate. So it's kind of an impossibility result. It tells us we cannot send more than this amount of messages at a higher rate than this. Okay, so that's nice, but it's only a one-sided bound. But it turns out we can also get a very similar bound in the other direction. Now there is some messiness, some epsilons and deltas that are kind of needed, but essentially it's the same quantity. Oh, and the other thing is that here it's still a replacer channel, but it's a replacer that just destroys the correlation between the two states. So it's actually the marginal of the actual output that is written there. So this is also the mutual information asymptotically, right? We had these two definitions of mutual information, one with the minimization over sigma and one without. And in here we also kind of see these two. And so this is now bound in the other direction. This means that this can be achieved. So there's an actual code that achieves this. And in this sense, this result is tight, right? We have an upper bound and a lower bound in terms of essentially the same quantity. And so hopefully now we can just apply what we know about hypothesis testing and compute some asymptotics, which is almost true. It almost works. There's just one difficulty, that if I plug in n instead of 1, so if I look at n copies of this channel, then I can just apply this one-shot result and just have a larger channel that is comprised of n copies of the channel. The issue that I get, though, is that actually the achievability is just fine. But here, in the converse, I have this maximum over input states. And if I have n copies, then this maximization is actually over input states on n copies of the channel. And I could have entanglement between all of these. And that is what kind of creates all these problems we have with, well, problems, these superadditivity and so on occurs. We have very nice one-shot bounds, but when we try to analyze them asymptotically, it's not as easy as you might think. You run into the problems there because you need to optimize over all possible input states. Okay, but at least for the achievability bound here, we can choose the rho A for the lower bound, and we can immediately get the asymptotics using the hypothesis testing results. And what are those asymptotics? Well, they have been around with us for some time. So, for example, the initial result by Bennett et al. Showed that this limit here indeed goes to what we call the entanglement-assisted channel capacity, which is just a maximal mutual information. So this formula looks exactly like the classical channel capacity, which is why it's so nice. So if we allow entanglement assistance, we kind of recover the simplicity of the classical capacity formula, of Shannon's formula. And at least in one direction, this bound immediately follows from this one shot. As I said, in the other direction, the situation is a little bit more complicated. We can also write this in a slightly different way as an expansion. For that, we need a little bit stronger results, because here, when we need this limit epsilon 0, this is called a weak converse. So we just know that if we don't allow any error, then this is the maximum that can be achieved, the maximum rate that we can achieve. The strong converse tells us that even if we allow some constant error, we still cannot achieve more than a higher rate than the channel capacity. So then we kind of get an expansion with a small o. And the question is, can we do more? And it turns out that for some channels we can do more, but I'm just going to explain it maybe in the case of classical quantum channels. There we can do much more refined analysis. And so pictorially, what comes out is something like this. So here you just see on one axis the error, on the other axis you see this rate at which we can send information. So if this rate has this transition point here at the channel capacity, so asymptotically, as n goes to infinity, if you are below the channel capacity, then the error can go to 0. If you're above, the error will necessarily have to go to 1. And so that there's this transition, phase transition, if you will. But if you look at smaller n, then you see that this transition is actually smooth. So there's this Gaussian approximation, which shows you the dependence between these different things. So one thing you can learn from this is, for example, that if your encoder or decoder can only deal with 40 qubits at most, then you probably should look at this yellow curve here and not at the channel capacity. This will give you the trade-off between error and error and rate, even for optimal codes. This is for optimal code still, but even then you cannot achieve the capacity if your decoder can only measure 40 qubits. So that is maybe the lesson to be learned from this. Okay, so yes, I mean we can write this as an analytic approximation formula, which follows essentially from the same type of arguments we've seen with hypothesis testing. So this would be the corrections to Stein's lemma, and the capacity comes from Stein's lemma in hypothesis testing. Good. So maybe just to mention another area of progress. So we have nice one-shot characterizations of these two-terminal problems, so-called two-terminal problems, where we have one sender, one receiver. But as soon as we kind of look at more complicated settings, like, for example, in this room, right, if everybody's trying to communicate with the Wi-Fi antenna, I mean, for those who were able to get any Wi-Fi access. And so the antenna has to communicate with lots of people at the same time, but all these signals are kind of overlaid. So in practice, we often have problems where there are multiple receivers, multiple senders. And in that situation, there is very little known, actually. I mean, there are many open questions in classical information theory and even more in quantum information. So this talk at this QIP it concerns one particular problem, which is the multiple access channel, where there's one receiver but multiple senders. And that is at least asymptotically understood, but they derived some nice new one-shot inner bounds. Good. So now the final part, randomness extraction. This one I also chose, well, because I worked on it myself, but also because there is some nice progress at this QIP on this topic. So randomness extraction, I'm just going to give a very brief introduction of what it is. So we have some joint state between, that has a classical quantum structure. So there's some random variable x that is correlated to a quantum system B. And our goal is that to remove this correlation, essentially. So we want to extract from that a state or a random variable C that is now close to uniform and independent of B. So this is the task of randomness extraction. Now there's a seed involved, and I'm taking expectation over this seed because the function can use some randomness itself. Doesn't need to be a deterministic function. And so we want to understand this problem and find trade-offs for this. So what are the trade-offs here? Well, we can choose, we have maybe two parameters that we're interested in. One of them is the error, so how close we get to in trace distance to this state that is perfectly uncorrelated, uniform and independent of the side information. That's one parameter that we want to optimize. And the other is the length of the string that we extract. Okay, if the length is 0, then obviously I can always do that with 0 error. Don't need to even do anything. But as the longer my random string should be, the more difficult it is, and maybe well, obviously there are some limits of what is possible. So that's a trade-off that we want to look at. There are other things that we would want to consider in practice, like how much seed that is needed to do this. But that we will ignore here. So then I'm just looking at this boundary again, very similar to the boundaries that I've discussed before. So we're trying to find the maximum length in I think I chose it in bits, such that the error is bounded by epsilon. And this quantity one can characterize in terms of smooth min-entropy that I introduced. So that's one way to characterize it. There are many variations possible on these bounds. But the point is, this kind of gives the one-shot characterization of it. Now, here in cryptography, often we are actually happy with that, and we don't go any further into asymptotics. The reason is that in cryptography, often the IID assumption, so that we have independent copies of a state, is completely unjustified, or we don't want to assume such a structure of the source. So in that case, the best thing we can do is these one-shot bounds, and then we kind of have to deal with these quantities and find some ways to bound them. But still, we might be interested to understand if these bounds are actually tight, at least in the IID setting. And so maybe that's for cryptographers less interesting, but for information theory, it's still a very relevant question. So we can define this length ln epsilon, which is the same as before, but now I just allow n copies. So we take n copies and try to extract a random string from those. and these are IID copies. And then I'm asking the same questions, like how does this length now scale when I increase n? And what we can immediately see from the results that were written down on the previous slide on this one-shot bounds is that asymptotically this will converge to the conditional entropy plus some correction term that is square root of n. Now this actually uses a result that I didn't discuss, which is called the asymptotic equipartition property of the smooth min-entropy. It says that the smooth min-entropy for IID states converges to just a conditional entropy, so this conditional entropy, which is kind of a variant of the Stein's lemma, but for smooth min-entropy. You can think of it that way. We can actually relate smooth min-entropy to hypothesis testing and then just apply Stein's lemma. But there are different ways of showing this. But the point is we get an expansion like this. So what this tells us is that asymptotically, the amount of randomness you can extract from a source is given by the conditional entropy. Okay, because the conditional entropy, you say it tells us something about the uncertainty that here an observer with access to B has about X, and that tells us how much, if the uncertainty is larger, then it means that there's more randomness that we can extract. Now, the issue with the bounds that I presented before in terms of smooth entropies is that if we try to do higher order expansions, we run into some troubles. The reason for this is subtle, and this is kind of, I mean, it's one reason why I find these kind of things interesting, because if you want to do these expansions, you need to really have really clean proofs. And here we have a little issue, because on the one side, we have a 2 square root of epsilon. On the other side, we have an epsilon minus delta. The minus delta is actually not a problem for the second order result, but the square root of epsilon will show up in the asymptotic expansion. And so if we use these bounds here, we wouldn't actually find out exactly what this O of square root of n term is, but we just get bounds on it. So that's not very satisfactory. But it turns out that a very recent paper that the paper is given here. Actually, there is multiple authors. I guess I wrote Hoeffding because he sent me the draft of it. We can have an expansion of this problem now. So this is very recent, even after the QIP deadline. There is an expansion for this problem in second order, but it doesn't actually go via smooth entropies, it goes via hypothesis testing more directly. So luckily, this problem is now solved properly. So we understand the asymptotics of this problem up to the second order term. And again, essentially it's the corrections to Stein's lemma that come in here, but they're interesting in the sense that we are interested in the optimal trade-offs. It kind of tells us how much randomness we can extract, even in the optimal case where the eavesdropper behaves in an IID fashion. So in practice, it might be even less randomness that we can extract because the eavesdropper might act in a correlated way, but at least this gives us some fundamental limits that we cannot overcome. Okay, and then finally, there are 2 papers at this QIP that discussed the error exponents for this problem. So we have seen The error exponent problem is slightly different, and there we use different results from hypothesis testing, but they're all very related. So here, we are actually fixing the rate at which we extract randomness. But and then we are interested in how the error behaves. So we fix the rate, and obviously we want to choose R to be smaller than the conditional entropy. Otherwise, this will not work. But if you choose R to be smaller than the conditional entropy, then we expect that the error goes to 0, right? Because we can extract the conditional entropy. If we go below with our rate, the error should go to 0 exponentially, hopefully. And so we might ask, okay, so what is exactly the exponent with which it goes to 0 if you use an optimal extractor? And this, I think, is now solved, although I need to speak to the authors, because when I was preparing this, I saw two different bounds. So one of these papers gives an upper bound, one of them gives a lower bound. They look different, but I think they are the same due to some relation between entropies that I didn't mention in this talk. But the point is, these are again optimizations over now conditional Renyi entropies, where you can see that at least two of the definitions that we discussed, well, didn't discuss, that I just threw at you, appear in here, and so they have meaning. Yeah, so it's not 100%. I need to verify this again to see if they really match. So at least we have an upper and lower bound, I think, and we're getting close to solving this problem, which is nice because it gives an operational meaning to these sandwiched Renyi conditional entropies. Okay, so these are two, I think it's a merged talk, this QRP. Okay, so maybe quick break for questions. I don't know, how much time do I have left? 15, okay. But yeah, so maybe it's a good time for questions, and then I have some open questions to end with. Okay, no questions, that's also good. Then I have questions for you. So these are just some of the things that are still open in this field. I mean, it's a selection that is not meant to be complete, but it's maybe things that I'm interested in. I mean, I mentioned already some during the talks. So here, one of them is, I mentioned at some point there is also conditional mutual information, but I didn't talk about it anymore in the quantum setting. The reason is that in the quantum setting, it's actually quite complicated, and we barely understand the asymptotic quantity, the conditional asymptotic conditional mutual information, which we can write down. I mean, it follows. We can define it via essentially these expressions here, which are the same relations we would have classically. So we can define this quantity, and it seems to have very useful properties and appears also in operational problems as an asymptotic rate, mostly because in those operation problems, actually this difference here appears, the difference of the two conditional entropies, which is this, how we define the conditional mutual information. It doesn't have this nice formula in terms of the relative entropy that we have classically, but still, this quantity seems to be the right one, and we understand it. The issue with it is it's actually, if you think about what kind of operators appear in it, it's 4 different non-commuting operators that show up. So we have the state rho ABC of the 3 systems, and then I have 2 marginals, A, C, and B, C, that appear here as separate entropies, and then also the marginal of C appears again. So these are 3 different density operators that don't commute. So you saw before, even for 2 densities that don't commute, there were many ways in which we could rearrange them in different definitions of quantum relative entropy. Here the problem is we have 4 of them, and we have no idea how to order them. We know how to order them at alpha equals 1, so to say, so in this conditional mutual information here. But if we want to define a Renyi version of that, then we quickly run into trouble. So there is no definition known that seems to have all the properties that we kind of hope for. There are various suggestions that have been made, I mean, and discussed. So there's a paper suggesting different possible definitions and exploring their properties, but there's no conclusive answer what the right definition would be. And I mean, how would we even know that something is the right definition? Well, for that we would kind of need to understand maybe some error exponent, right? We need to understand the error exponent of a task that is characterized by the conditional mutual information, and if we then can express the error exponent as an optimization over some Renyi conditional mutual information, then that's probably a useful definition. But yeah, we don't really have any of that. And it seems hard to make progress on these questions even without having a definition first. So usually it's easier to solve a problem if you know what the result should look like. So this seems to be, yeah, this is still been open for some time, and I think would be interesting to think about what exact properties such a definition must have, and yeah, how it should be then defined. So for example, you expect mutual information to have a data processing inequality that if you apply a map to either A or B, but separately, not a joint map, either system A or B, then the mutual information should decrease or not increase. Right? By doing local operations, you cannot increase the mutual information. So this is what classically certainly holds. And it should also hold for a Renyi version of this. But as far as I understand, the definitions that have been proposed only satisfy this for one of the systems. So you can either define it such that the A system satisfies data processing or B, but not both. So that's one of the questions that I think it's necessary to find this definition to make any progress. So if you have any ideas for this, that would certainly be helpful. Now, another kind of open problem that I think is really looking for a solution and should be somewhat in reach, one would think, is this question of the error exponent for classical quantum channels. So for classical quantum channels, we know almost everything. They behave almost as nicely as classical channels. So we have this quantum output, but somehow we can deal with it. We need to use quantum hypothesis testing instead of classical hypothesis testing, but everything works nicely because we don't have this optimization over entangled input states. It's just classical inputs, and things work out nicely. The only question that we haven't really found an answer to is this error exponent. So this is the question of what happens if we transmit information just slightly below capacity? And if we are slightly below capacity, we expect the error that we incur to go to 0 with an exponent that classically is known. But in the quantum case, we don't have matching upper and lower bounds on this exponent. And the problem seems to be that there's some matrix algebra that is missing that we will need to prove this. But yeah, it has been elusive for now. But yeah, even at this QRP, there's some progress on error exponents. So maybe the tools are actually around or at least close. So if you're interested in quantum Shannon theory, this would be like a question that I think hopefully can be solved in the next couple of years with the right idea. Okay, so then a final one, which is an open problem that we had in one of our papers. I kind of alluded a little bit to it. We discussed entanglement-assisted coding, and we have these nice one-shot results that they really look like the asymptotic result, except that the D is replaced by a DH epsilon, so this hypothesis testing quantity instead of the relative entropy. And so one thinks that the one-shot bounds are as tight as they can be. And we can also analyze them in the first order to get the right capacity, so the entanglement-assisted capacity. But if we want to get corrections to it, then this doesn't work yet. So there is an optimization over entangled states, also in the entanglement-assisted capacity, which we can kind of get rid of it, but we lose too much when we do that. And when we compute our asymptotics, so we lose something that would impact the second order term. So there seems to be, the right tool seems to be missing to analyze this. One can look at this using Definetti theorems and so on, but it destroys the second order term. And so we don't have a second order expansion for this problem. There's also moderate deviation expansions for these channel coding problems, which we also here don't have for the same reason. So this also seems like something, maybe it requires an interesting new technique, but it seems to be in reach. It's maybe a bit more specialized result, but I guess one reason why I'm interested in these results is because they seem to require new techniques. So I'm more interested in the techniques maybe than the results itself. So having these higher order expansions means you need to have a really tight analysis, which requires new techniques, which then often can be used for very other, completely different problems, maybe not even in quantum Shannon theory. And so I still think that a lot of technical input into the field can come from quantum Shannon theory, even though maybe the actual problems that we're trying to solve seem quite specialized. But the toolkit that is developed to do so is useful all around quantum information theory. And so with that, I actually would like to close. And thanks for your attention.
Are there any other questions?
Yeah, so the delta is kind of,
Repeat the question, please.
oh yes. So yeah, in some of the results, maybe I just show one, it's easier. Like here, for example, right, we have this delta occurring, and the question was, well, what is this delta doing there? It's not operational, right? The epsilon has operational meaning. That's the thing we want to fix. The delta is just some additional parameter that we can actually optimize over. So this holds for all delta between 0 and epsilon. So we want this thing to be positive still, and this should not be 0, otherwise the bounds diverge. But we actually optimize over this. And that's usually, so this doesn't disturb us too much. We can do the asymptotics, then choose delta to be like a 1 over square root of n or something. Then we just get a log n term here, which we don't care too much about. So that's why I didn't talk about it. It doesn't bother us too much usually.
Other questions? Great. So let's thank Marco again.